right, everybody, welcome back to our translations discussion. So you'll notice I already have quite a bit prepped here. So we're going to continue talking about more translations, and I'm trying to structure this very similarly to the way that we structured the vertical translations conversation. So we started with a function. This time we're looking at f of x is equal to the square root of x. Not a shape we've worked with a lot, so I'll say a couple of words about it. And then here on the right, I've already indicated the domain and the range of this function. We'll mention a couple of things about that too. And then the function that we're going to be working with, which is this new transformed function, g of x is equal to the square root of x minus 2. So we have our point chart here, and we have our think about question. What does the graph of g of x look like? Now, since we haven't worked with this graph a ton, I just wanted to say a couple of words about it. Oh, we don't need this extra 0, 0 down here. So notice that this is the square root graph. You cannot take the square root of any number less than 0 as far as our functions are concerned, because the square root of a negative number is non-real and our functions don't output non-real numbers. So you'll see that the very, very, very leftmost point on the graph is 0, 0. And then up here, if you take the square root of 1, you get 1, so we have 1, 1. Here, if you take the square root of 2, well, the square root of 2 is not a rational number, and you can see it on the graph. It's between 1 and 2, but it's not quite 1.5. So it's not a super nice point to graph, but there it is. And then if you go all the way over here, since the square root of 4 is actually a nice number, right? It's just 2. That's a much nicer point to graph. So I'm actually going to erase the square root of 4, and I'm going to put 2. Okay? And I think that's one of the things that I'm going to try to sort of remind you throughout this process, that when you're working with square roots, the square roots of perfect squares are nice numbers. So it's nice to try to look for, graphing purposes, looking for inputs that will generate nice outputs. Which takes us over here. So I'm going to switch to blue, this beautiful blue color. And we're going to build a points chart for our new function g. Now, our function g is the square root of x minus 2. And we just said that our functions that we work with cannot handle square roots of negative numbers because those are non-real. So the very smallest input that I can possibly take is 2. And then we'll just take a few more. So let's take 3, we'll take 4, and then we'll also take 6. And I think you'll see why I'm picking 6 and skipping 5. Okay, so here goes. So 2 minus 2 is 0. The square root of that is just 0. So the point that will be on the graph is 2, 0. 3 minus 2 is 1. The square root of 1 is 1. So that's the point 3, 1. And then 4, 4 minus 2 is 2. So you see there's the square root of 2 again, which is not a rational number. So that's, again, one of those points that's not super nice to plot. And I hope that that also shows you why the next value of x that I picked is 6. 6 minus 2 is 4, right? And 4 is a perfect square. It's just 2. Or I should say the square root of 4 is 2. So that actually gets us a nice point to plot. Okay, so let's go ahead and plot them. So there's the point 2, 0. There is the point 3, 1. I'm going to skip 4 just because it has that yucky square root as its y-coordinate, and I want to focus on my nice points right now. So there is 6, 2. And what I'm hoping you see, so I haven't drawn in the graph yet, but what I'm hoping you're already kind of starting to see is that the blue points are flashing out a shape identical to this black shape, but shifted to the right. So let's go ahead and draw that in. Right, so again, graphs are not perfect, but they give us the general idea, right? By the way, as I'm kind of drawing this in, remember that you don't have to use these 4 values. You can use any values you like. The only consideration that you might have is you are plotting them on a graph, so you don't want to use too big. And also, of course, the domain, right? The fact that g of x cannot handle any input less than 2. Beyond that, you can pick any values you want, really. Just 2, 3, and 6, you'll notice, are kind of favorites for this sort of thing, for this particular function. Now, I'm not going to label it on the graph very carefully, but see, look at this there. This point, this blue point, do you see how its y-coordinate is a little bigger than 1, but not quite 1.5? Well, that's the square root of 2. And I'm not going to label it because I don't want to get my graph too claustrophobic, but this is why I didn't plot that point. It doesn't have a super nice y-coordinate. Okay, let's get rid of that straight mark. All right, so now that we have the graph, let's maybe go over here to our think about question. What does the graph of g of x look like? Well, what do you think? Well, it looks just like the graph of f, just shifted to the right 2 units. So let's write that here. Just like the graph of f, shifted to the right 2 units. Okay. All right, so I want to look at a little bit more and then summarize and actually look at another example. So what I want you all to notice is that for any point I take on the blue graph, if I dot over until I come to a point on the black graph, every single point has a corresponding one on the graph of f where the y-coordinate is the same, but the x-coordinate is 2 units smaller. For example, here, there's 3, 1. If I dot over to the left, there's the point on the graph of f, and its y-coordinate is also 1, but its x-coordinate is 2 smaller. By that same token, here's the point 2, 0. If I dot over to the left, there's the point on the graph of f, same y-coordinate, but the x-coordinate is smaller by 2. In fact, this is true for any point on the graph of g. So if I pick some random point right there like this, I'm specifically not choosing it to have anything nice about it. So the x-coordinate is something, it's just x. The y-coordinate is always the output that this function assigns to the input x, so that's g of x. And if I dot over, there it is, right? There is the point on the graph of g, and I hope you all can see, you can actually see it. The x-coordinate is 2 units less. We went over 1, 2. So the x-coordinate is x minus 2. Now, this is a point on the graph of f. Every point on the graph of a function is an input-output pair. So the y-coordinate is f of x minus 2. But these 2 points have the same y-coordinate, so I'm going to write that down here. So we see that f of x minus 2 is equal to g of x. In other words, replacing x with x minus 2 results in a shift to the right. By 2 units. Let's take a second to just kind of acknowledge this in the domain and range conversation. So this transformation only affected x coordinates. You can see the y coordinates of all the points stayed the same. It's just the x coordinates that shifted over. So when we look at the range of the new function, that has not been impacted. It is still from 0 to infinity, right? We see that here. The lowest point on the graph still has x-coordinate 0. Whereas if we look at domain, well, we can look at the graph. The first point on the graph, the leftmost point, has x-coordinate 2. There are no points on the graph whose x-coordinate is less than 2. So the domain starts at 2 and then keeps going from there. So I want you to notice that the domain is also shifted to the right. All right, so this is our first example. For our second example, we're going to go to the next page where I already have kind of a lot prepared for us. So same thing, we're still looking at g of x and f of x. F of x is still our original function, it's the square root of x. This time g of x is the square root of x plus 3. So you see here, I've already got your little think about question, what will the graph of g of x look like? So think about that. Given what we just said with the square root of x minus 2, what do we think the square root of x plus 3 is going to look like? All right, well, here goes. So we're going to build another one of those tables. So it'll be 3 columns. There. So these will be our x values. Here we'll compute our g of x's, which is the square root of x plus 3. And then here we'll just write the point to keep ourselves honest. All right, I'm going to zoom in. I like the way my writing looks better when I zoom in a little bit. Okay, so here goes. So again, it doesn't matter what x values you pick, but you want to be mindful of the domain. So the square root of x plus 3, our functions only deal in real numbers, so you cannot have a negative underneath the square root. So the smallest value of x that you could possibly take is negative 3. And then we'll go from there. So maybe we'll take negative 3. Let's take negative 2. And then we'll take 1. I'm just going to take those 3 values, and you'll see why in a second. If you want, you could add more, and I'll say a few words about that in a second. All right, so if x is negative 3, g of x is the square root of negative 3 plus 3. That's just 0. So the point there is negative 3 comma 0. If x is negative 2, negative 2 plus 3 is 1. The square root of 1 is 1. So this is negative 2 comma 1, and then 1 plus 3, that's 4. The square root of 4 is 2. So I think you all can see why I picked those 3 values, because they're the ones that resulted in nice perfect squares underneath the square root. Okay, here goes. So I'm going to plot these points. So we have negative 3, 0. We have negative 2, 1, and then we have 1, 2. Let's label them. Negative 3, 0, negative 2, 1, and 1, 2. So again, I hope that even though we haven't drawn it out yet, that you're already starting to see that the blue points are fleshing out a shape that's identical to the black shape, but shifted to the left this time. All right, so I'm going to draw it in. So here we go. Again, graphs are not meant to be perfect. They're meant to convey a general idea. Right, so that's pretty good actually. Now, just real quick, if you wanted more points, you can have more points. So of course, this graph goes on forever. If you want to indicate that, you can put a little arrow on it. But if you wanted, you could do more points in our table here. So rather than stopping at 1, you could have done more. So for example, if x were 6, right? 6 plus 3 is 9. That's another nice perfect square. So 6 is another great candidate for a point to plot. I'm not going to plot it, but, you know, you can see it's up here, right? 6, 3, be up there. Just very gently put it there. I'm not going to worry about it, though. All right, so again, there's nothing special about the values I picked. I just wanted to get a shape fleshed out. Same thing. every single point on the graph of G, if I want to, I can dot over from it and end up with a point on the graph of F. So I started at 1, 2. If I dot over to the graph of F, I end up at the point 4, 2. Same y coordinate, but the x coordinate is 3 bigger. If I take the point negative 2, 1, and I dot over until I get to the graph of F, up, same y coordinate, and the x coordinate is bigger by 3. If I start at the point negative 3, 0, and I dot over from there it is, a point on the graph of F, same y coordinate, the x coordinate is 3 bigger. So in general, if I take some random point on the graph of G, like this one, let's call it x comma g of x, I can dot over from there to the graph of F. And I hope you can see, like, all of the little dotted lines that I've drawn in are the same length, because every single point got shifted the same way. So the x coordinate here is x plus 3. It's 3 bigger, just like 4 and 1 and 1 and negative 2. Now, the y coordinate is the same as the y coordinate of the blue point, but it's also a point on the graph of F. So it's also f of x plus 3. So just like in our last example, so we see that f of x plus 3 is equal to g of x. In other words, and I'm going to write the same thing out that I wrote on the last example. In other words, replacing x with x plus 3 resulted in a shift to the left by 3 units. Okay, cool. I will actually leave it to you. I'm going to leave a little empty box here, and you can all fill this in for yourselves. What about the domain and the range? Oops. Of G. Okay, so you can think about that for yourselves. Of course, I'm hoping that you're saying that this is very similar to the example we just did. This transformation only impacted x coordinates, so the range should be unchanged, and I'll let you think about the domain. All right, so I just want to make one last summary statement, and we're going to call this lesson over. So summary. Starting with a function f of x, and replacing x with x plus c, where c can be any real number, will result in a shift horizontally, a horizontal shift. If c is greater than 0, the shift is to the left. If c is less than 0, the shift is to the right. So this concludes our second translations lesson. So we talked about horizontal translations in this lesson. We started out with a translation to the right and then a translation to the left. And in the next lesson that I will make for you, we will look at a few examples that combine vertical and horizontal translations. That's all I got for you for this time. See you later. Bye.